Okay, so what this did for us, it created a scatter matrix where we have rows and columns are the features. So we have income, years experience, and IQ for our rows, and same thing for our columns. And so we can see some relationships. For example, income and IQ, we can see this scatter plot here. We can see that there's a slight upward trend. It's a bit messy though. And then we have years experience. That looks like a solid trend for income. And then we have, of course, in the diagonal, the histograms, because we don't need to see the direct relationship between IQ and itself, for example. And so that shows us the distribution, while we can also see these relationships. Again, notice that we don't have the date of birth in here. That's because it's not numeric, it's in date time. In order to actually work that out, what we need to do is use our age. So in feature engineering, we can create that, and then we can come back and replot this. But before we do, let's do one more exploration. We're going to create a heat map. So for that, we're going to import Seaborn. If you don't have Seaborn, it's extremely easy. All you have to do is pip install Seaborn, and that's it. If you're using Anaconda, you can also do conda install Seaborn. Okay, so what you see here is that we're going to create a heat map of df.core. This gives us a correlation matrix. So it's going to help to illustrate any relationships and their strength. So we create that plot, and this gives us IQ, years experience, and income. We're really only concerned with this bottom row here, where we have the correlation between IQ and income. We can see that that's somewhat strong. It's maybe roughly around 0.4. Years experience seems to be the strongest. We're going to ignore the income portion because income obviously will have a perfect correlation with itself. So years experience looks like that's pretty high up there as far as the correlation goes. And again, we don't have age yet. So let's go ahead and move on to the data processing. So for data processing, and go ahead and ignore what we already have for the train evaluate models. For data processing, we're going to create the age, and then we can go back and replot those things. For this, we're going to import the datetime module. So from datetime import datetime, we're going to do that as dt. So we'll create the age column. And here what we're doing is we're using the pandas apply method, and we're just creating a simple lambda function here. So we're going to map each value of x from the date of birth column, and we're going to use the dt.strip time, which is the string parse time, so strp time. And then we'll use the same year from the data that was when the data was collected or created. So we're going to use 2017 10 31. And then we need to pass in the format. So for here, we're going to do year dash month and day, and that's all we have there. But of course, what we need is to extract some other values from it. So we need to do minus x. We want to get the days. So this subtraction here, this will create a time delta. And so we want to get the days from the time delta and divide by 365 to get years out of that. So that'll give us the age of this person. So again, x is the date of birth, and so we're going to subtract the date of birth from our current date, and then we'll divide by 365 of the days. That'll give us our age. And let's go ahead and drop the date of birth column because we don't need that anymore. So here we're just specifying that date of birth is in axis 1 because going down the rows would be axis 0. We're going to go across the columns. And then in place, make sure that it drops it without just returning a view. And then let's take a look at the top of this new data frame. So now we have IQ, years experience, income, and age. So we're good to go there. Let's go back up and replot these. So now our scatter matrix also includes age. So if we were to look at the income portion, we can also see a somewhat positive relationship with income. And then in the heat map, looking at income, we can see the age is not as strong. It's about the same as IQ, and years experience is still the strongest, has the best correlation. And so at this point, we can move on to training and evaluating our models. We're going to do this using TensorFlow. In a previous video, we created a really simple linear model, but that just had the one parameter. It was a single value for W because it was just y equals mx plus b. In this case, we have data that has three variables, our IQ, years of experience, and age. So let's create a multivariate model. In this case, we're not going to be doing ordinary least squares regression because that's entirely different from something you do in TensorFlow. But what we can do is still create a multivariate linear model, but train it using a gradient descent optimizer. So creating our model, first thing that we need to do is actually do a train test split of our data. So in this case, what we're going to do is we're going to create X and Y. We're going to separate those out of our data frame. So we have this df.iloc, which we're going to be basically using index numbers in order to slice things out of here. So we're going to take all rows, and then we're going to accept only columns 0, 1, and 3, which are the IQ, years experience, and age. And then for Y, we're just going to get the age column. From there, all we have to do is create an index for our sample, which Pandas makes it extremely easy to sample data as well. All we have to do is pass in the frac argument, which is the fraction or proportion of the data that we want. So we're going to take 67% of it, and the index will make sure that we only get index values for that. And then we can create the train and test. For train, we just need to filter all values that are within the index for our train index. And then in the test, the little tilde here tells it to do the negation of this. So instead of having X index is in the train index, we're going to take all X values where their index is not in the train index. The dot values on the end just ensures that we get numpy arrays, which we can use with our TensorFlow. So we do something similar for the Y here. Okay, so let's make sure, even though we did it up above, let's just make sure we have TensorFlow imported. Now we're going to create those. And here we have create model. So this is where we're finally going to build off of what we did before. By the way, the TensorFlow reset default graph, so tf.reset default graph, that's useful if you haven't been using something that we'll cover later, which is called variable scope. So for example, without something that we're just calling variable scope right now, if we were to create this and if we were to run this cell and we came back and we for some reason needed to make a slight edit somewhere and rerun it, we'd get an error because we already have this variable named W. And so the reset default graph basically just clears everything for us, and so we can start fresh. So we don't need to call it right now. But in this case, let's take a look at our model. Before, as mentioned, we only had a single value for W. We just started off with 0.1. But in this case, we want to create our variable and set its initializer to a column vector that has all 0.1. We could start off with 0.0. I just chose 0.1. And so this column vector is going to give us our weights for our three values, our three features that we're training on. And then of course we have our parameter b, which is our intercept. And as before, we're just going to set our initializer to a scalar value, and it'll be 0. And then, of course, we need the placeholders, and that's for inputting our data as well as the labels, the proper values that we're going to be training against. So our linear model this time is slightly different. Instead of just having before where we had w times x plus b, we now have matrix multiplication required, and then we're also going to reshape the data after that's all done, just so that we have a flattened vector. So we have the TensorFlow matrix multiplication, that's the matmul, and we're going to multiply w onto x. So w is a column vector, and then each x is going to be a vector. So it's going to be a 1 by 3 and a 3 by 1. And then we're going to add b to that. And in the reshape, we're reshaping it using -1. -1 just means use all the dimensions that are left, or sorry, the remaining shape. Whereas, so if we do -1 comma and leave that blank, that means it's going to reshape it to the length of the output, and it's just going to be one-dimensional. And of course, we give our name y hat. So let's go ahead and call that. And so now that creates our graph for our model. And then as before, we've already gone over creating our root mean squared error that we're going to use as a loss function, but I've simplified it this time. Last time it was good to have 3 lines. It helped to show you what we were doing. But this time we can just use the reduce mean to create MSE, where before we created SE, MSE, and then RMSE. And then this time we've added one more thing, the test NRMSE. So that's the normalized root mean square error. That helps us to kind of understand the scale of things. So we normalize it by dividing RMSE by the mean of our y values. That just gives us a scale to work from so we can understand the error in relation to the values that we're actually predicting. So in this case, we just have the tf.divide, and we're dividing RMSE by the absolute value of the mean of y. We just call the absolute just in case. We want to make sure we don't have any negative values in there. And of course, we need to initialize our variables and then run the initialization. So we create the init object, or the init node, using the variables initializer. So we need to initialize w and b, and we'll run that initializer. And then here's our training. You'll recognize this from our previous video also. I've changed the learning rate, so now instead of 0.01, we have 0.001. Learning rate can matter a lot. If you want to, you can play around with that value and see how things change. Again, we're using the gradient descent optimizer. And so this time we're going to run through 800. So our loops will loop through. It'll basically be like 800 epochs on a neural network. And then we have something slightly different here. So if I mod 50 equals 0, so basically every time we've gone through 50 iterations, then what we're going to do is we're going to compute the normalized root mean square error on our test data. So here we'll do nrmse equals ses.run test nrmse, that's our function, and then here's our feed dictionary where we're going to feed in the test values, xts and yts. And for each of those, we'll print out what that score is. Now, the I greater than 0, that's just because I didn't really want to print out the value for the very first run, so we'll just bypass that one. And if it's not in that, then this is where we'll be performing our training. So this step essentially skips training briefly, just for one step every 50, and then we return to the training itself. And this part, actually, we want to exclude that for now, and we'll get to that in a bit. So here we'll run on the train function and xtr, ytr. So the train being this node right here. All right, so let's go ahead and run that and see what happens. So we can see the test normalized root mean square error starting at 0.17, and it looks like it's actually not really going anywhere for us, at least not after 50 iterations. So let's go ahead and see what our parameters are. You know, the problem actually, I just realized that I accidentally typed age for our Y where we want income. So let's go ahead and reset that. And now is a great time to have our tf.reset default graph. Just go through these again. Okay, let's try that once more. And that looks a lot better. Now we can look at our parameters. Okay, so the learned parameters are 0.27, which is pretty close to 0.3, 1.46, close to 1.5, and then we also have 0.91, close to 8.3. Not perfect, obviously, but neither is the data, and we don't have a lot of it. And then there's the y-intercept. That should be plus 5, but we're getting 0.02. Sometimes the y-intercept is actually the hardest part to get from a linear model. So overall, we're doing pretty good. Let's finish off this example by completing our objective. If you'll recall, our objective was to infer the relationships between the attributes of interest and the annual income of people. So in this case, we have for IQ, since income is measured in thousands, for every increase of 1 point in IQ, we have an increase of approximately $270 annually. Whereas for every additional year of experience, we can expect a person to earn an extra $1,400 or $1,460 a year. And then for age, for every additional year a person is, so every increase in age by 1 year, we can expect an additional $900 in income. That's what our model is telling us. And then next we can move on to TensorBoard.